Here is a question that I'd like us to consider as we learn the contents of the video. Neural networks consist of complex building blocks which have been interconnected in simple ways. Is the statement true or false? Let's now really hone in on the role that neurons play in the learning process. The nodes in the computation graph are really just neurons. Each individual neuron only performs very simple operations on our data. These neurons, however, are connected in very complex and sophisticated ways. This is an important point to keep in mind. Each individual neuron is really simple in its working. What makes the neural network as a whole complex is the interconnections between those neurons. And those interconnections vary a great deal based on our application. For instance, convolutional neural networks are a type of wiring up of neurons which tend to be used for image processing applications. On the other hand, if we were going with a text processing or a natural language processing application, we would more likely go with a different type of neural network called a recurrent neural network. And the big difference here would be in the manner in which the feature data is represented and in which the neurons are connected in the corresponding neural network. Indeed, when actually using neural networks in real life applications, the challenge is architecting the neural network, making decisions about the different layers and how they will be connected to each other. The typical unit of abstraction is a layer because a layer consists of groups of neurons which perform similar functions. All of the complexity in neural networks is in the interconnections. The individual neurons really only apply two simple functions to their inputs. The first of these is known as an affine transformation. This is simply a linear transformation, very much like linear regression. The second of these is an activation function. This helps to model nonlinear functions like XOR or logistic regression and so on. Let's now hone into one single neuron. Let's understand the operation of one single neuron. As with any neural network, there are going to be a bunch of inputs into this neuron. Let's call it x1 through xn. Those inputs will then be multiplied by weights w1 through wn and then added to a bias that is b. And indeed, this transformation is known as an affine transformation because we are taking an input vector x, multiplying it by another vector w, adding a bias b, and this is the affine function that gets passed to the activation function. That's the second step in the operation of a neuron. An example of a common activation function is something known as the ReLU. This stands for the rectified linear unit. The ReLU will return the maximum of its input and of 0. So if we pass in the output of the affine transformation, that's wx plus b, the output of a ReLU activation function will simply be max of wx plus b and 0. Now, the exact transformation that we apply in the activation function might change. The exact values of the weights and the biases might change. But at heart, each neuron is only going to carry out these two functions, one after the other. Let's understand this in a little more detail. Focus on the inputs. Here we have a lot of x values, x1 through xn. These represent potentially a feature vector. These are the features of whatever problem instance we are seeking to work with. The output from the activation function is the output of the neuron as a whole. There are different activation functions which are used in different use cases. The affine transformation and the activation function collectively define the neuron. So, training a neural network refers to the process of nailing down the values of the parameters in each of these functions. For the affine transformation, the parameters are w and b. So, this is just a weighted sum with a bias added. Those weights help the neuron to adjust the amount of weightage given to different features in the feature vector. The values w1 through wn help accomplish this. The value b just gets added on to the output. It's independent of any of the input features, and so it's called the bias. And once again, we should be absolutely clear on where the values of w and b come from. The answer is that these are determined during the training process. This is true of all implementations of neural networks, specifically in TensorFlow. W and B are variables. Note this again, W and B are variables, not placeholders and not constants. and the actual values of W and B are determined by TensorFlow during the training process. We shall see how that happens in more detail when we actually implement linear regression. The point about W and B being variables is an important one because these are going to change during the training process internally within the graph. The objective of the training process is going to be to find the best values of W and B for each neuron. And how are those best values going to be found? Well, you as the programmer are going to have to specify a cost function and an optimizer and a number of steps. You also have to point TensorFlow to your corpus of training data. Then TensorFlow will take care of a good deal of the plumbing for you. It will run the optimizer in order to minimize the cost function, and it will do so with different subsets of the training data, the corpus of training data, and it will execute as many optimization steps as you allowed it to. Each of these steps will cause the values of the variables W and B to change, and at the end of it all, those will represent the best possible values. This entire process is the training process. The training process might be simpler or more complex depending on the configuration of our neural network. Because neural networks can have different configurations and the interconnections in some of these can get very sophisticated, the training process can also take a long time. But the basic idea is the same. TensorFlow is going to run an optimizer, usually specified by us, to minimize a cost function, also specified by us, over a corpus of training data, specified by us, and do so for a number of iterations that once again we specify. Now, clearly, during the training process, there has got to be a feedback loop. The output of deeper layers in the neural network will need to be fed back into those of the earlier layers in order to find the values of W and B in those earlier layers which work best. This process is called backpropagation and is pretty much the norm, the standard way of training neural networks. By the end of this training process, the values of the weights and the biases in every neuron in our neural network will have converged to the best values. And in this way, the training algorithm will have told our neuron which of the values of the inputs matter and which do not. That's because a high value on a particular W coefficient implies that our neuron is giving a high amount of weightage to that particular input xi. On the other hand, if one of the W's has the value of 0, that just means that the neuron is completely ignoring the corresponding X input. And the bias is added on kind of exogenously to the product of W and X. So this acts as a correction. Now, if we specify the cost function for the affine transformation to be minimizing the square of the errors, that's the residuals, we basically just get linear regression. This shows that it's entirely possible for an affine transformation to learn a linear function, but in order for this neuron to learn a non-linear function, in other words, for the output of the neuron as a whole to be non-linear, we've got to generalize it. Thankfully, this generalization is pretty easy, and this is where the activation function comes into play. There are a bunch of common activation functions which have been found to work well in different applications. One common one is the ReLU. This is the max of 0 and the input. ReLU, which stands for rectified linear unit, is extremely commonly used as an activation function. Later, when we are talking about implementing logistic regression, we shall consider another common activation function called softmax. As the designer of the neural network, you get to pick what activation functions you would like your neurons to have, but all of them have the same basic idea. The activation function is needed for the neural network to model nonlinear functions, and this is accomplished by chaining the output of the affine transformation into the input of the activation function. Let's return to the question we posed at the start of this video. This statement is false. Hopefully, we've learned enough to see this for ourselves. Neural networks consist of building blocks called neurons. Each neuron is actually pretty simple. It just carries out an affine transformation followed by an activation function. Each of these neurons is individually pretty simple, but it's the interconnections between large numbers of neurons which give neural networks the ability to reverse engineer even complicated functions. And so this statement is false. It gets it exactly backwards. The individual units are simple, it's the interconnections which are complex.